This video is on section 5.1 from the Blitzer Precalculus textbook on verifying trig identities. And the idea on this one is to change one side of an equation, only one side, to make both sides equal. And if both sides are equal, that proves that it's an identity, meaning that it's true in all cases for the angles, for the angle that would be used. Now, sometimes you can do it with two sides, but when you do, you only work on one side and don't cross over to the other side. You work on that side completely independently and the other side completely independently from each other. We'll do an example of that as well. When you do this, you use normal math and algebra techniques as well as the various trig formulas. Those trig formulas are in the textbook as well as they're on a form here that I'll use to point things out. And we'll be talking about this one as we go through. All right, now, going through, what I want to do is I want to show you some of these techniques in the examples that are in the textbook. Each of the examples pretty much has something or shows you something about it. So, for instance, if we take a look here in example 1, when you see here, they use the trig identities and formulas, and they change secant and cotangent to something new, and then they cross things out. So what they're doing here is they're doing a basic algebra thing that you've done for a long time, reducing, a basic math thing. You're reducing or canceling something out. And so I will put a little note here. So in example 1, it shows that you're reducing, or in this case, fully canceling. And in example 2, let's take a look at what that one shows. In example 2, you have a place right here where you have sine squared x and cosine x plus cosine x. And then it shows in red that you're multiplying by cosine x over cosine x. Well, that's just the number 1. You're just simply multiplying by 1. But by doing that, you're able to get the same denominator on the bottom. And that allows you, because you're adding fractions, it allows you to add them and add together, or add the numerators. You have to have the same denominator in order to add fractions. So by doing this, you get a fraction that has the same denominator. So let's write that down, that you're multiplying by 1 in the form that's useful for you to get the same denominators so you can add or subtract fractions. In example 3, we see that it's using basic factoring. Let's take a look at that. Really basic, but very important factoring. You see here a cosine x minus cosine x sine squared x. There's a cosine x in each term. So you can take cosine x out of both of them, and that means you have to have a 1 here. But now you do. So this is taking out a common factor. And taking out a common factor, when you do that, this is one of those identities, the Pythagorean identity. 1 minus sine squared x is the same as cosine squared x. So when you then multiply it, you get a cosine cubed x, and that's what you were trying to get to. In order to do it, you have to take out a common factor, change that one, and then multiply these again, and you get that. So here you can see that taking out a common factor is a technique, the important technique to use. Taking out a common factor. In example 4, we have another thing. Let's take a look at what happens here. This, by the way, is on page 548, and you'll see example 4. And they have this set up, and they have two completely different denominators. So what they do is they find the lowest or the least common denominator, and in this case that means using the cosine x over here, so you multiply by cosine x over cosine x, and you multiply by 1 plus sine x top and bottom on this one. So this gets multiplied over here, and this gets multiplied over here, and voila, you have the same denominator. You have a mess of stuff up here in the numerators too, but you have the same denominator. And so you can add the fractions, which means keep that denominator, and then you can add all this stuff together, and that's how you do the rest of the problem. Okay, so down here at the bottom, by the way, once again, that they took out a common factor, and then they were able to cancel something out. So this used 3 different techniques that we were just talking about. Using the least common denominator, taking out a common factor here, where you took a 2 from both of them, and then reducing something because they're the same, and that gets you to a much smaller thing to work with. And then finish with that problem. So in example 4, you see least common denominator. You see a common factor, and you see reducing, canceling. Reducing, canceling. I really only focused on least common denominator in a way, but hey, this is definitely a part of that. All of them get used in that one. In example 5, there's another technique now that you have used and earlier this year as well. Here we see this one to verify this one, and you see 1 plus cosine x. Well, what you're able to do is multiply, they say by 1 minus cosine x. Notice it's the same. Well, they just took this first part. They're only working on the left side. And what happens, if you notice, is that this is the conjugate. So what we're doing is we're rationalizing it. Remember that term when we did it with square roots and we did it with the letter I. And that allows us to do it as an a plus b and an a minus b. Multiply it out, the middle terms go away, and you're squaring the 2 terms with it as a negative. So you can work it out as a FOIL type method, and you see that the middle terms go away. So that's rationalizing with the conjugate. And sometimes you have to do that too. Rationalize with a conjugate. And that allows you at that point, you then have a Pythagorean identity that you can change it with and continue to work. So let's take a look also at example 6. And example 6 is not necessarily a algebra math technique. What it is it reminds you here that changing to sines and cosines is an important step to do. In fact, I'm going to go further with that, and I'm going to say that changing everything to sines and cosines usually is the first best step to do in all of these verifying identities or any of these kinds of problems. Not always, but I would say a huge amount of the time, this is the best place to start because it simplifies things a great deal, allows you to cross things out more. You can see many of the identities a little bit easier. Not always, again, but I would say, I'm going to say 75 to 90% of the time, this is the way I would start a problem, and probably the main way, probably more than that, probably much closer to 100%. Okay, change everything to sines and cosines. However, be flexible and go with the problem. And that's the real key to these types of problems. You need to look at a problem, and play with it in your mind. Think about things you can do that would be a direction to go when you start changing some of the functions that you see, or start applying some techniques to it, because you might find you get stuck and it didn't work out doing it that way. So go back and try a different thing, or partway through it try to change something a little bit. So the real key idea is to be flexible and notice I guess you'd say parts or patterns. Parts or patterns. you're going to start noticing whenever you have a squared one, if you have a 1 plus cosine squared, 1 minus sine squared, anything like that, those are indications, and secant squared, tangent squared, and cosecant squared, all of those too, are often indications that you can use a Pythagorean identity. Not always, but sometimes. So there'll be some things you can do with that. Okay, there's a review of some of the examples and gives you some idea of where to start with verifying trig identities, or some of the things you would do with them. Now let's go through one of the examples, or an example for it, and I'll call this is still 5-1, and this is Roman numeral 2, and let us verify sine theta over cosine theta. Oops, nope, not cosine, this is cotangent. Please change that to cotangent. So sine theta over cotangent theta minus secant theta is equal to negative cosine theta. So what we want to do, here's the equal sign, what we want to do is to work on this side in order to get it equal to that side. So what I'll do is I will start here. When I look at this, I see a sine, but I see cotangent and secant. So I'm going to start right off with changing those into sines and cosines. So I have sine theta here on top. Cotangent is actually cosine over sine. So I'm going to rewrite that as cosine of theta over sine of theta. And subtract it, well, secant is the same as 1 over cosine theta. Those are ones you should remember. You shouldn't even need them on a paper, but they are here on this one to remind you. So when one of them was secant, so secant is 1 over cosine, and cotangent is cosine over sine. These you should know. These are ones you should know cold, and not have any problem remembering to do them. Now we can do some various techniques. One of them is to deal with this kind of a fraction. Remember that this is actually sine theta over 1 and cosine theta over sine theta. So the way to handle that one is to multiply top and bottom. Let's do it with that sine of theta. So I'm going to multiply, because you can't have, well, you can have, but I really don't want you to have, and you don't want to have, this kind of thing where you have a fraction in a fraction. So we get rid of it by multiplying by the denominator here. Notice what I'm doing is I'm multiplying by 1. Sine of theta over 1 divided by sine of theta over 1. So sine of theta over sine of theta, that's equal to 1. So I'm just multiplying by the number 1. But I'm multiplying by 1 in a format that allows me to cancel this out. And when I do that, when I cancel that out, on the top I get sine times sine, so that's sine squared theta. On the bottom, I have cosine theta, so that's sine squared over 1, but we don't need to show the 1 underneath the fraction, or as part of the fraction. And this one, we don't have to show a 1 under that. So therefore, we have sine squared theta over cosine theta, minus 1 over cosine theta. Still is equal to negative cosine theta. But now this is a little bit cleaned up, okay, because you notice we have the same denominator, and we're subtracting fractions. So let's rewrite it showing that. The next thing, if you notice now, this one is a Pythagorean identity. Sine squared theta minus 1. Well, wait a minute, is it really? Take a look over here at the Pythagorean identities. And notice that one of these Pythagorean identities is sine squared theta plus cosine squared theta equals 1. This is not in the same format, but it's close to it. Notice we have the sine and cosine together. So let's change that. Let's move the sign over. In fact, over here, I'm going to write that. I'm going to put a line here and make this, when I come back to here, I'm going to do a little work here. The Pythagorean theorem is, or identity, the Pythagorean identity is that sine squared of theta plus cosine squared theta is equal to 1. So here I have the sine squared with the 1. Well, I could bring 1 over here and make it minus 1 and bring that over there, but then it would be negative cosine squared. I could do that. Yeah, actually, so there's two ways to think of this. Let's do this one. Let's subtract 1 from here. So if I subtract 1, and if I subtract cosine squared theta from both sides, I'm going to get sine squared theta minus 1 is equal to negative cosine squared theta. So this and that are equal. I can just take it away and put in negative cosine squared theta. There's another thing that I want to show you though, and I'm going to do that sort of the hard way here so that you can see it, is let's come back to here. I'm going to subtract sine squared theta and bring it over here. Cosine squared theta is equal to 1 minus sine squared theta. Well, that and this are almost the same, except they're not, because here the 1 is positive and here it's negative, and here the sine squared is negative and the sine squared is positive. But you are allowed to take out a negative 1 from both of these and take out a common factor of a negative 1. In other words, why don't we rewrite this as negative 1 times negative sine squared theta, and then let's do this plus a negative 1 is negative 1, right? Well, actually what I want to do, if you think about it, that's negative 1 plus 1. Well, let's see, if I were to take that out, that means, and so I have this here. So I have a negative 1, and I have a negative 1, and I have a term here and a term here, and every number has a 1 in front of it. So that negative 1 is actually 1 times negative 1. So there's a little 1 here, just as if this was plus negative 17, we'd have a 1 in front of it. Or if it was plus 84, we'd have a 1 in front of it. Every number has a 1 in front of it. But I now have a common factor of negative 1. So I'm going to take that out. And that gives me negative sine squared theta plus 1, because we're taking negative 1 from here, so the hidden 1 no longer is hidden. I don't like to write it with the negative first. Let's switch these around, because as long as I keep the negative in front of the sign, I'm good to go. I can switch it then. So I can rewrite that as negative 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta, so I can put that in here and get negative cosine squared theta. So I can do that, and taking out a negative 1 or rewriting it with negative 1s so that you can take out a negative 1 is a good technique to do. However, if you recognize instead, let's do a little squiggly line here. If you do like I did here and bring the negative 1 over and the cosine squared over is negative, you don't even have to go through that work in this problem. You can see, or in a problem like this, if you see that the signs are reversed, just redo the Pythagorean identity by bringing the 1 this way and the cosine squared that way, and you can put negative cosine squared theta there. So that's a simpler method. It may or may not be easier to remember. This method works for other things other than sine and cosine, so that's why I wanted to show it to you. But for what we're doing right now, that's probably a good way to think of it. That instead of rewriting it this way or make it 1 minus, rewrite it by bringing the 1 here as a negative 1 and that one is a negative cosine squared, and then put it in place. So this top part becomes that, and I have cosine theta underneath is equal to negative cosine theta. So doing that work or this work allows me to get to here. That becomes this. Well, cosine and cosine squared, that's like one of these and two of these, so that's going to reduce. So we're going to take that and cancel it. So the cosine theta here, because really what's happening is you have a negative cosine squared theta times the cosine squared theta over, oops, nope, it's not squared anymore because I just took the square out. This would be like 49, so it's 7 times 7. Negative 49 would be negative 7 times positive 7. And if I have a 7 down here, I would cancel out a 7. So now I take this negative cosine squared and do negative cosine times negative cosine, not a 2 up there, or 1. And the cosine underneath here will cancel out with that. So now I get negative cosine theta, and we just proved that this is an identity. So that's sort of the answer, except the whole work is. So on a test, you would have to show, if it says verify, that means you have to show the steps that get you down here, that get you to where the two sides are equal. And here is one example of doing it. I'm going to show you another example. I'll call this one's 2A, and let's do 2B as another example. All right, let me walk you through this one. So this one's going to have some more stuff in it, but it's not really going to be harder. It's not going to be anything harder about it, it's just going to have more. So let's verify this one. And it's going to be parentheses 1 minus cosine squared theta, close parentheses, secant theta, cotangent theta, plus tangent theta, secant theta, cosine squared theta, equals, and I almost ran out of room, I should have started over sooner, but I think I'll just get it, and equals 2 sine theta. So that's what we're going to try to get to over here. We're going to work with this side to try to get to that. So we're going to take each one of these things, or figure out what to do. There's a plus here. So what we have is we have two terms. And this term has 3 things in it, and this term has 3 things in it. 4 actually, because that's a square. This one's one thing, counts as 1. So let's look at it, because what you want to do, you want to change everything to sines and cosines, but you also want to look at what you see. And I see one of these ones with something squared, and that makes me think we could have a Pythagorean identity, and we do indeed. Because here, if I subtract cosine squared theta from this side and bring it over here, I get 1 minus cosine squared theta. And that's the same as sine squared theta. So I will start right off by changing that to sine squared theta. Secant of theta is the same as 1 over cosine theta. Cotangent, these are like multiplying in between. You don't have to show the dots, but you can. Cotangent has cosine over sine. That is one of these tangent-cotangent identities. Cotangent is that. Cotangent is also 1 over tangent, but in this case we want it to be cosines and sines. So we're making it cosine and sine. And then plus, well, tangent will be sine over cosine. Too bad that's not multiplying, because if that was multiplying, we'd just cancel out the sines, cancel out the cosines. Oh well, ooh, looks like we'll be able to do that in a minute. Secant is 1 over cosine, again, and cosine squared is actually just still cosine squared. Might as well just leave it. And that's still going to be equal to 2 sine theta. Sorry, I'm writing that so small. I didn't leave myself quite enough space there. Now we can start doing some of this canceling, because for instance, that'll cancel with that, that'll cancel with one of those. So I have sine of theta here, plus, looks like these 2 cosines are going to cancel out with both of these, because that's cosine and cosine. And we're going to be left with sine theta here. And that's going to be equal to 2 sine theta on that side. But wait a minute. One of these plus one of these makes 2 of them. So if that was like x plus x, you'd now have 2x. So sine theta and sine theta, you now have 2 sine theta, which happens to be 2 sine theta, and we just verified it. Yay! So that looks like a mess to start off with, but once you change everything and cancel it out, it's not a mess at all. It actually turns out to be a very easy problem if you pay attention to what you have and change the things, and then start canceling. So 3 parts to it is paying attention, or recognizing, noticing the things that you have, like this one, changing each of them to something simpler, and secant, cotangent, cosecant, tangent, always changing them to sine and cosine is usually considered simpler. But that allows you to cancel out a whole bunch of stuff here, just like that. That worked really well. There are other ways to do these, by the way. The first problem in this one and all the other ones you see, most times there are steps in there that you could go a different direction, and do different things with and still get down to the same answer as long as you do steps correctly and do things right. So I could have maybe tried changing all of these to secants and cosecants, and it might have worked out just fine too, actually. It probably could have all worked out. It just would have been a different way to do it, and it's not a right or a wrong. I personally think it would have been longer, but that's not wrong. Okay, so that's the second example for that. Now I'm going to do a problem where it's both sides being done. However, I'll tell you that you have to remember the very important part about not crossing over. So this is still 5-1. And we're going to verify this identity by working on both sides. So if you're told to do that, then you're not only allowed to, you have to do something on both sides. But, and this one's very important, do not cross over. And the reason is because you don't know yet its identity. You're trying to verify it. So it's an equal sign in between it, and you're trying to make sure the two sides are equal. By moving something to one side or to the other side, that means now you've sort of muddied up the waters, and the equal sign doesn't mean the same thing. It's not that you're trying to prove they're equal anymore. That's what verify means. Prove these are equal. Well, if you start moving things from side to side, you're not proving it anymore, you're pretending it already is equal. And you can't pretend it's already equal. You have to prove it's equal. All right, so let's write this down, please. Tangent squared theta plus 1 over sine theta times tangent theta times secant theta plus 1 equals secant squared theta minus tangent squared theta. So this equal sign means, if it's verify, it means let's make sure this side and this side are equal. You have to separate them completely because we don't know for sure they're equal, and only by getting this side moved down to something and this side moved down to something and having them be the same, only then do we know they really are equal. So let's find out, or let's do it. So I will do different things. I'll start off first by looking at this and seeing, one of these setups that might be a Pythagorean identity, and it's an exact one. I don't even have to add or subtract anything. That's secant squared theta. So I'll change the top to secant squared theta. And underneath it, I still have sine theta, but tangent I will change to sine theta over cosine theta, and this is like it's 1 underneath. You don't have to show that, but it won't hurt. The secant is 1 over cosine theta, and then we still have a plus 1 here. Now, notice that plus 1 is separate from all these that are multiplying, so it's almost like you have to multiply those things, then add 1. It's not secant theta plus 1. If I had put parentheses around that, it would be a different thing. But there aren't parentheses around it. I'll check, make sure. Nope, there's not supposed to be parentheses. But that would really change what you do with this, and in this case, not an issue because it's not parentheses, it's separate. So order of operations is you do multiplying before you do adding if we knew numbers. That does allow us to do canceling out of some things or not canceling out in others, so let's see what happens here. Now, you can, when you do this, work on one side for a while and then go to the other side and work on that and see if they're starting to meet, or you can just do like one thing on each. It really doesn't matter, but I think I'll just sort of work on both at the same time here and go back and forth. Secant, oh, well, again now, I'm going to change both of these, secant and tangent, to sines and cosines. So this one I'll do 1 over cosine squared theta, which you just learned something, that if you have a squared one, you can still use the normal properties and change them to the others, just keep it squared. So if that one's squared, then this one's going to be squared. Now, tangent squared then would be sine squared theta over cosine squared theta, because tangent is sine over cosine. This one helps, immediately I like the fact that I have the same denominator here, so I'm going to do cosine squared theta, and I'm going to do 1 minus sine squared theta, and I like this fact. Notice this now, if that's an identity. You look at the Pythagorean identities, that's cosine squared theta. Ooh, I really got to start on this side, because on this side it comes down to 1. Cool. Well, that means the other side has to come down to 1 too. So now I know where I'm going, I guess, but hopefully I can get to it from this. So let's work with this one. So I'm going to do this. The secant, now that I changed that into secant, now I'm going to change secant into a sine or a cosine. And secant is the same as 1 over cosine. Oh, wait a minute. I made a mistake. Did I make sense? No, I didn't. It is secant. Yep, it is secant. Okay. So that's 1 over cosine squared theta. Good. Let's do that. Okay. Now, let's take a look and see what I can do with this. I have sine times sine, which is sine squared theta, and cosine times cosine, which is cosine squared theta, and plus 1. Now, if I didn't have that plus 1, I'd multiply top and bottom by cosine squared theta and just cancel it out. But because of that plus 1, and this is grouped when it's inside, when it's underneath, when it's all being divided by that, then all this is grouped. So I have to do something with that. I can see what to do. I'm going to take that 1 over cosine squared theta, and sine squared over cosine squared is tangent. Remember up here we took this tangent and changed it to that? Well, it looks to me, since we have this, we can change it to tangent. So this is a case where we're not changing it into sine and cosine, we're changing it into tangent, which usually I wouldn't have said is the best thing to do, but it clearly is here because that's a Pythagorean identity. We can let that be the secant squared of theta. So now I get 1 over cosine squared theta over secant squared theta. Ooh, this is actually secant squared theta. Remember that from before? So it looks like I'm going to have to change that back to secant squared theta. I didn't need to change that to 1 over cosine squared theta, but at that time I didn't know that. It might have been more useful to have it there, because usually it is. In this case it wasn't, but it doesn't hurt. I can go ahead and change that to secant squared theta, and then the bottom secant squared theta, and that is 1. So we get 1 equals 1. Yay! We have to go down further on this side, but we did indeed get 1. So notice all the techniques we had to use. First, changing everything to sine and cosine. We didn't know we needed to. We didn't need to on this one. Using the Pythagorean identity when we see it. Not just multiplying them there. Here, another Pythagorean. Oh, and doing this where we subtract a fraction. Using a Pythagorean identity, canceling out, or reducing rather. And down here, using a Pythagorean identity. Oh, this was changing the form. Using let's see, that was a reciprocal. No, that's a tangent identity. And not so bad. So this looks like a mess to start off with. It looks like that's going to be really hard. But once you start changing things, and if you recognize, especially the Pythagorean identities, those are really vital. Very, very vital. Recognizing that makes a huge difference. Okay, now you see how to do that type of problem. So here in section 5.1, let's quickly review what this section is all about here. In section 5.1, we have the techniques shown in the textbook that you can use in different problems, depending upon what you see. And then we did this problem where it showed some of the techniques that you can use, which in this case allow you to get the 2 sides equal. This problem where just changing everything into sines and cosines made it much simpler. In fact, that really made it easy. Only one Pythagorean identity to do. And this one, to do both sides, but to do them separately and get them to where they come out to the same thing. They're not always 1. You more often will get something like negative sine squared theta here. And over here, then you'd work till you get negative sine squared theta. Or maybe you get 3 tangent cubed theta. And here you'd end up getting 3 tangent cubed, or something like that. Who knows what it'll come to. And that's just it, as you don't know yet. You just keep working on both sides until you get something where they're both equal. All right, and by using the things that you've learned, you're able to do that. and that's section 5.1.